morning we have been discussing macro bicyclic cryptands. So, today we will discuss another type of compounds where you have bridged aromatic hydrocarbons. Okay. They are called cyclophanes. So, the cyclophanes, they have bridged aromatics and so that their cavity is hydrophobic in nature. Cavity will be very much hydrophobic, that is one point. Cavity is hydrophobic. Cavity is completely hydrophobic. When we discuss cryptand, I told you that in cryptands cavity can be hydrophobic as well as hydrophilic. So, we can play around. Okay. One side of the cavity can be hydrophobic, another side could be completely hydrophilic and all that, and it has donor atoms and all that. But in cyclophanes you have completely hydrophobic, and because it is aromatic bridged, so the cavity is very self persistent. That means, shape of the cavity will not change and it can discriminate non-polar guests depending upon the size of the guest and size of the cavity. So, sometimes there is a oil spill, you have to remove that oil spill. So, we can that time we can use cyclophanes. So, cyclophanes are also very important macrocyclic and macrobicyclic compounds. What I will do, I will not discuss synthesis of these cyclophanes. They are similar to when we discuss synthesis of macrocycles or macrobicyclic compounds. So, these are also similar. So, that is why I am not going to discuss them, but I am going to write some structure and see. Okay. So, let me draw some structures, a representative cyclophanes. For example, these are interesting looking structures. But the architecture is very similar to your cryptands, like it has also a cavity and it is also tricyclic, bicyclic, tricyclic, so on. Let me draw this. Okay. And so, these beautiful structures. Well, the one that I have drawn is not that rigid, as you can understand, because there is this aliphatic chain. If the CH2N is very large, then it may not be as rigid as we desire. And here N is 5 and 7, they are known 5 and 7, but it is a typical cyclophane. Another cyclophane can be, this cyclophane is very interesting. is quite a tedious job for me, because I have to draw many structures. Okay. Okay. So is here. All right. We are almost there. NH and I will show you some absolutely rigid structures are also. So, these are typical cyclophanes, and as you can see, the cavity is hydrophobic. This one is not absolutely hydrophobic, and if we protonate this compound is not totally insoluble in aqueous medium, but this but soluble in organic non-polar solvents. This compound is similar, but if I protonate that, suppose I protonate that with an acid, then it will become NH2 and then it will become positively charged. In that case, in that situation, it will be soluble in aqueous solvents, soluble in water or aqueous solvents, and so in that case, if some organic compounds, non-polar compound is dissolved in aqueous solvents, this cyclophane can extract that, depending upon, as I told you, cavity size and the guest size matching, must be there. Okay. So, these are biphenyl moiety is very common in cyclophanes, and these are also for a from aqueous medium. If I want to extract an organic compound from aqueous medium, biphenyl methane moiety is quite common in common moiety in cyclophane. So, this is okay, and then CH2N, NH, and as I sometimes manage with cartoon, here also I will manage with cartoon. We do not have too much time to play around with writing structures. Okay. So, these kind of compounds can be made soluble in aqueous medium when the nitrogens are protonated under acids. Okay. So, these can be water soluble cyclophanes. So, these not only this one, but another one, these are quite interesting things. Okay. Another one, here okay. Okay. NH CH2N and then NH, this is CH2, CH2N and then again NH. Now, I will do now I will do cartoon. See this one? If you look at cryptand structure, this is also like a cryptand, except that this particular one is insoluble in water. They can be made soluble in water on protonation, and they like organic guests mostly. Here is one interesting cyclophane. This structure I will write completely. This is an interesting cyclophane. Sometimes it is difficult to manage without writing. Okay. One, two, three. Okay. Then I will write it's not really good looking. One, two, three, 4, 5, 6. Hang on. Okay. And then here 6. It's quite interesting compound. Let me draw. Okay. Okay. Now 1, 2, 3. Then this aromatic is not very good. I will draw it better. It's tough, difficult, not very easy. One, two, then 3. Meta. So, this one what happened? 1, 2, 3, 4, 5, 6. Okay. It will go here. Yeah. So, this is also another very interesting 3-dimensional, and it has no choice. It cannot form, cannot form any protonated form, because there is no nitrogen to protonate. So, however, it has a, you see, it has a 3-dimensional cavity and almost circular. I have my drawing is very bad. So, that is why you may not be able to see the circular, but trust me, it is like a circular with 4 aromatics, and even it can accept a metal ion, because metal can also complex with pi cloud. We know in organometallic chemistry that metal ion can combine with aromatics, they can bind aromatics, okay, with pi systems. So, metal pi interactions is also known in organometallics. So, in similar fashion, this particular cyclophane can accept metal ions depending upon its size and matching, size matching. Finally, I will show you one more interesting cyclophane. It's very difficult to show you, but still I will try. I am not going to be discouraged from writing. Okay, no problem. Okay. Then I never practiced this thing before, so it is quite difficult to write. But you know, a good chemist should be a person who can write good structures. So, okay. And here and here. Okay, so All right. So, I got it. So, this cartoon means these are aliphatic chains, it can bind through any of the aromatics. So, this looks like this is known as tryptophan, that is why I took so much time and writing this. Tryptophan. Okay. So, therefore, what we know, what do we know so far, that in addition to cryptands, macrobicyclic cryptands, we have cyclophanes, which are very similar in structures, okay, very similar in structures, and they are insoluble in aqueous medium, but can be made to solubilize in aqueous medium if there is NH groups are there. However, if not, then they are absolutely insoluble, but they can accept guests, and those are important guests, important compounds. Suppose there is a oil spill in ocean, some localized. So, I have to get rid of those hydrocarbons. In those cases, we need some host that will complex these hydrocarbons and remove from water, so that water will be pure. So, these are not useless stuff, but they are very, very useful. Okay. And finally, once I get out of this cryptans and related compounds, I will discuss about another very important compounds, series of compounds which have seen an explosive growth in the last 5-10 years. They are called self persistent organic cages. Okay. There is a subtle difference between cryptands and self persistent organic cages. Let me draw one of them. I will draw only one, and then I will make cartoons only. O, O, O. Okay. Then okay. Then what? Then I can make another compound, another aromatic. It could be meta, it could be para. Actually it will be like this. Well, I am having some problem in writing this, but tell you what, I will explain it, and then another day I will write these structures. What happens is, exactly like cryptan, as we showed earlier times, usually they have aromatic bridgeheads, and aromatic bridgehead, I am having problem in writing. Okay, I will not try anymore. They will fix it, then we will see. So, what happens? You have aromatic bridgeheads, and you have 3 arms or 3 bridges attached to the aromatic bridgehead. Because it is aromatic bridgehead and the 3 bridges, they also contain aromatics. So, as a result, the particular compound, although it is like a cryptand architecture, it is non-flexible. This is absolutely non-flexible. That is why whether you put a metal ion in or not, it is always keeping its shape unaltered. That is why it is called self-persistent organic cages. What is the difference between self-persistent organic cages and cryptands? In a cryptand, when a metal ion goes inside, then some of these donor atoms in the bridge, present in the bridge, they can move around little bit, not much, little bit, and so that these donor atoms can wrap around a metal ion, okay, nicely. But in this case, that is not possible. When you put a metal ion or leave it empty, the shape is not going to change, and that is why it is known as self-persistent organic cages. I will take it from here, from next class. Thank you.